In this section, we're going to look at a remarkable sequence of numbers. It looks like this: 1, 1, 2, 3, 5, 8, 13, 21. Now, the way I'm getting these numbers is in the following fashion. If I take two previous numbers and add them together, I get the next number. So look, if I do 1 plus 2, I get 3. If I do 2 plus 3, I get 5. 3 plus 5 is 8, and so on. You can see, so 13 plus 21, that'll end up being 34. And then 21 plus 34 is 55. And then 34 plus 55 is 89. 55 plus 89 is 144. 144 plus 89 is 233. And so on. So you can see how this works. So we define the first one, F1 to be 1, F2 to be 2, and then actually F2 is defined to also be 1, and then F3, the third number in the list, is 2. So at this point, we were able to do F1 plus F2 to get that 2. Then if I move on to F sub 4, I'm going to take F sub 3 and add it to F sub 2. So where's my F sub 3 is 2, and my F sub 2 is 1. So that equals 3. F sub 5 equals F sub 4 plus F sub 3, which is, the F sub 4 was 3, the F sub 3 was equal to 2, and you get 5. So you can see how you generate them this way. In general, the formula looks like this: f of n plus, well, let's say 2, that equals f of n plus f of n plus 1. You'll see different formulations. It just depends. So just as an example, if I want F13, that equals F11 plus F12. So let me come up to my list and see where 11 and 12 are. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 89 is F11. 144 is F12. So I have, well, I did this one already. So we have 89 plus 144 is 233. If I wanted to do F14 to find the next number, that'll be F12 plus F13. F12 is 144. F13 we now know to be 233. And it looks like 377 is our next Fibonacci number. Now, interestingly enough, do you remember earlier in the semester we did something called successive differences? Well, when I try to do it for this sequence, watch. I'm going to start 1, 1, 2, 3. I was counting instead of actually paying attention. 2 plus 3 is 5. 5 plus 3 is 8. 13. 13 plus 8 is 21. 21 plus 13 is 34. 34 plus 21 is 55. And then I had an 89. So let's use the method of successive differences to find out what number would be next. So we typically do this. We subtract. There's a 0. There's 1. There's 1. There's 2. 3. 5. 8. 13. 21. 34. You see, this list here has no, I don't see it, an arithmetic progression or a geometric progression down here. In fact, if you look, the same numbers appear again as originally. So I'm recreating the Fibonacci sequence. So in order to do this using successive differences, well, we would have to know that the next number is 55. Well, that's that guy right there. And the reason you would know that is because we've already done the sequence, and you can see that these numbers are being the same numbers as the original sequence itself. And so you would do like we normally did. I take my 89 plus 55 and I would get 144. But even if you keep trying to do these successive differences, you're not going to get anywhere that is meaningful, because you'll keep getting the sequence back you see that, how the sequence is generating again? So never is this going to get to a point where it's just one solid number all the way across. So this will just go on forever. So you have to come up with some other method of getting this number if you're going to use this method. Well, I guess the way I said that was wrong. If you're going to use a method like this, you're going to have to adopt something different, like the way I did, and looked to see that you were reproducing the sequence again to know what came next. This section is devoted to these numbers. So there are other patterns that have been noticed in these numbers, and I'm just going to list a few of them. Some other ones will be in the homework. If you look at the number 1 squared, that of course is equal to 1, but 1 also equals 1 times 1. That's f1 times f2. Now look at 1 squared plus 1 squared. That of course is equal to 2. Or if I want to write it in a more unique way, I could say that that's 1 times 2. So in that way I can think of that as f2 times f3. So now if I do 1 squared plus 1 squared plus 2 squared, I get a total of 6. But that's 2 times 3, which is f3 times f4. So on the left, what I'm doing is adding up the squares of the Fibonacci numbers. The next Fibonacci number was 3. So here I'm going to get a total of 15, which is 3 times 5. That's f4 times f5. In general, if you do f1 squared plus f2 squared plus f, say, n squared, you'll end up getting f sub n times f sub n plus 1. Another place where the Fibonacci numbers appear is if I take 1 and divide it by 89. You might remember that to do this requires that you do 1.0. In fact, you want enough zeros to make sure that you at least cover 89. So the way you work this is you bring that up, put a 0 out here, and now I look. Does 89 go into 100? It does, one time. Put a 0 here and a 1 here. Subtract and I get 11. Now you're allowed to bring down a 0 on these, and so 89 goes into 110 one time. Bring down another 0. I'm going to do this for a little bit. 89 goes into 210 twice. And then I have 32. Bring down another 0. 89 goes into 320 3 times. 3 times 89 would be 267. Bring down another 0. 89 goes into 530 5 times. 5 times 89 is 445. 85 is the difference. Bring down another 0. Now at this point I'm going to stop. You would do another digit, but look at these digits appearing up here. These are the beginnings of the Fibonacci sequence. Of course, the next number that I'm going to have to put is a 9, so it destroys it. But there's other places where you see it as well. Look at these numbers here. There's 1, 1, 2, 3, 5, 8. So you can see the Fibonacci numbers are staring right there. They just seem to appear in a lot of different things. If you look at the decimals that I did right last time, the 0.01135, actually the next digit after it would be a 9, but this will go on forever. That division will never stop. If you were to look down and do these digits, look what we have: 0.01 plus 0.001, 0.0002. So I'm doing the Fibonacci numbers: 0.00003, 0.00005, 0.0000008. So each time I'm putting in a Fibonacci number, but I'm adding a 0. So I'll put a 0 under the 8, and then I'll put a 13 after it. Put a 0 under the 1, and then the next Fibonacci number was 21. And this, of course, goes on forever. Now, if you were somehow to add this all up, this infinite string of numbers, you would end up getting the division that we just did. So you can see them. There they are. So the Fibonacci numbers just seem to appear all over the place. Remember, this is equal to 1 divided by 89. One of the most tantalizing aspects of the Fibonacci numbers are when we start looking at this kind of a ratio, Fn plus 1 over F sub n. Mathematicians have really been looking at that ratio to see if they can discover some very interesting things. So let's do a little practice with it. If I look at F2 divided by F1, that's 1 over 1, which equals 1. And then if I do F3 over F2, I'll get 2 over 1, and that's equal to 2. Then F4 over F3, that equals 3 over 2, which is 1.5. I'm interested in cataloging the decimals. F sub 5 over F sub 4, that's 5 over 3, which is 1.6 with a bar over it. F6 over F5, that equals 8 over 5, which is equal to 1.6. And then F7 over F6 equals 13 over 8, which equals 1.625. F8 over F7 equals 21 over 13, which is, now these numbers, I'm not going to be able to give you exact numbers, so these will be approximations to 4 decimal places. 1.6154, but that number does go on. F9 over F8, we have 34 over 21, and once again that's approximately 1.619. And then F10 over F9, that's 55 over 34. That's approximately equal to 1.6176. These numbers are actually approaching something. F sub n plus 1 over F sub n will actually approach, that's what this arrow means, the following number. 1 plus the square root of 5 over 2. That's actually what it's going to. As a decimal, that's about 1.618. And you can see the numbers, they're starting to get close to that as these get larger. This number has a special name. It's so special they give it a name. phi, the Greek letter phi or phi, depending on how you like to say it. This here is the Greek letter phi, but more important than that, it has a special name. It's called the golden ratio. The reason why they call it the golden ratio is it was a belief that if you were to create things, height versus width in that ratio, about 1.6 to 1, then that has the greatest aesthetic beauty, most pleasing to the eye. So in some of the art and in some of the construction that was done in the old days, in ancient times, tried to put the golden ratio in their work sometimes. For example, the Great Pyramid at, I guess this word is Giza. You can tell me if I made a mistake, but the way it looks, if you looked at the side of it, here's the size of this pyramid. If you look at it from the side, of course it looks like an equilateral triangle. But what we have, let me draw a line directly here. The height of this thing is 480.6 feet. Half of the base down here is 377.8 feet. This slant height, this so-called slant height here, 611.3 feet. So what we're looking at is the width is 377, if you will. The width to the middle is 377, and then this slant height, if you will, is this. Now, check this out. If I take 611.3 and divide it by 377.8, I'll get an approximate number, but let's go and bring out the calculator and see what it says. 611.3 divided by 377.8. Do you see the first three digits there? 1.618. I believe more than one pyramid actually has this property as well. It tells us that the Egyptians were well aware of this number, and they even tried to incorporate it into more of their construction. For example, I believe, well, actually, I have to correct myself. The Parthenon, I don't think is an Egyptian thing. I believe it is Roman, but they use a width to height ratio of about 1.618. Even today, if you look at our ratio in movie screens, it's not far off from the golden ratio if you look at the width to the height. There is one last formulation of the golden ratio, and it looks like this. Perhaps the earliest version was this. We'll call this the length, and we'll call this the width. So we want to set the length divided by width, so it's like a ratio, if you will, is equal to the length plus width divided by the length. Now there's all sorts of ways of solving this, and I don't require you to solve it. I just want you to see this. Here, if I split the fraction up on the left into two parts like this, I'll get 1 plus W over L, L over W. So now, assuming that L over W is in exactly the shape that I want, so let's say L over W has been given the golden ratio. So I'll replace it there. Over here, though, this is upside down. What you can do, though, is write this like that. So that's 1 over phi. Then I'm going to multiply the entire equation by phi. And then to solve an equation like this, you do the following. You subtract everything to the left side. And then we have a method for solving this, which is called the quadratic formula. You do not need to know that. But I thought you might like to see how it comes about. So according to the quadratic formula, the way we set it up is we do negative b. Remember, b is the number in front of phi. That's negative 1. So negative 1 is 1. Plus and minus. This gives two solutions. And then this negative 1, we square it to give us 1. Minus 4. This is just a formula. A is the number in front of here. That's 1. And this last number is negative 1. And then you divide by twice whatever number is in front. And that's just a 1. So I divide by 2. Now, oftentimes it happens in mathematics that we get more than one solution and we end up throwing away solutions that don't make any sense. So if you take a look, that's a positive number. That's a negative number. We do not want the negative number. That's not the solution. So you can see here how we get this. And this is from considering a length versus width scenario like this. The length versus width equals the length plus width versus length. This to them was the definition of the most pleasing relationship between length and width. One last note. In calculus circles, once again, we won't have to know this either, but in calculus circles, we'll write something like this. And it's known as a limiting number.